Welcome to Copernicus AI, Frontiers of Science. I'm Bella, and today we're diving deep into the fascinating world of neuromorphic chips and brain-inspired computing architectures. Brian, our expert today, what makes this area of research so revolutionary, and what paradigm shifts are we seeing?
Thanks, Bella. It's a pleasure to be here. The excitement around neuromorphic computing stems from its potential to overcome the limitations of traditional von Neumann architectures, which struggle with the demands of big data and AI. A key paradigm shift is moving away from sequential processing to parallel, brain-inspired computation. For example, research by Yi and colleagues, published recently and available on PubMed, explores post-silicon nanoelectronic devices specifically for brain-inspired chips. The traditional von Neumann architecture is showing limitations in performance.
So, what specific limitations are these chips designed to address, and how do they mimic the brain?
The primary limitations are the memory wall, the latency in accessing memory, and the power wall, energy dissipation. Neuromorphic chips aim to solve this by integrating memory and processing units, much like neurons and synapses in the brain. They use devices like memory stores, which can both store and process information. Yang and colleagues have published interesting work on the nonlinearity in memory stores for neuromorphic dynamic systems. Their research, also available on PubMed, highlights how these nonlinear properties are crucial for emulating the complex behavior of biological neurons.
That sounds incredibly complex. Can you give us a more concrete example of how this works in practice?
Certainly. Think about image recognition. A traditional computer processes an image by fetching data from memory, performing calculations, and then storing the results back in memory. This is repeated for every pixel. A neuromorphic chip, on the other hand, can process all the pixels in parallel, with each neuron in the chip responding to different features of the image simultaneously. This dramatically speeds up processing and reduces energy consumption. Zhang, Zhuohui Huang, and Jie Jiang discuss this in their recent paper on emerging photoelectric devices for neuromorphic vision applications. We'll link to that research in the show notes.
So, this is particularly relevant for visual processing. What other applications are emerging?
Absolutely. Vision is a key area, but the applications extend far beyond that. Neuromorphic computing is being explored for robotics, where real-time decision-making is crucial, for sensor networks, where low-power operation is essential, and even for simulating complex biological systems. Aidan J. Prendergast and colleagues recently published research on real-time generation of hyperbolic neuronal spiking patterns, which is fundamental to understanding how neurons communicate. Their work, available on PubMed, opens up possibilities for creating more realistic and efficient neuromorphic models.
You mentioned simulating biological systems. Does this mean we could eventually simulate entire brains using these chips?
That's the long-term vision, although we're still a long way off. Simulating a complete human brain is an incredibly complex challenge, but neuromorphic chips offer a promising path forward. The ability to model neuronal behavior more accurately and efficiently is a crucial step. However, mapping neural networks onto neuromorphic hardware is also a challenge. Song Wang and team have worked on this with their closed-loop mapping strategy for deploying neural networks on neuromorphic hardware.
So, what are some of the challenges in developing and implementing these neuromorphic systems?
One of the biggest challenges is the hardware itself. We need to develop new materials and devices that can mimic the behavior of neurons and synapses more accurately and efficiently. Another challenge is developing algorithms and software that can take advantage of the unique architecture of neuromorphic chips. Traditional programming models don't work well, so we need new approaches. Guanrui Wang and colleagues at AIL have been working on this, with their research on end-to-end implementation of various hybrid neural networks on a cross-paradigm neuromorphic chip. That's a mouthful, but the link is in the description.
Are there any other materials being explored for this?
Yes, absolutely. Kekin Liu and others have been exploring ferroelectric materials for multilayer reservoir computing, showing promise in temporal information processing. Xiaofang Luo and team are working on interface engineering in optoelectronic hafnium oxide-based heterojunction synaptic devices. These are just a few examples of the diverse research landscape.
This sounds like it could revolutionize AI, but what about the ethical considerations? If these chips become powerful enough to mimic the human brain, are we opening up a Pandora's box?
That's a very important question, and it's something that researchers are actively discussing. As these technologies become more powerful, we need to consider the potential risks and ensure that they are used responsibly. This includes things like data privacy, algorithmic bias, and the potential for misuse. It's crucial to have these conversations early on, before the technology becomes too widespread.
This is all incredibly fascinating, Brian. Now, looking forward, what are the next big breakthroughs we can expect to see in the field of neuromorphic computing?
I think we'll see continued progress in developing new materials and devices, as well as more sophisticated algorithms and software. We'll also see more applications of neuromorphic computing in areas like robotics, healthcare, and finance. And, importantly, more research into the ethical implications of this technology. We are in the early stages of this technology's development, so there are many discoveries yet to be made.
Thank you, Brian, for breaking down this groundbreaking research for us. It's clear that neuromorphic computing has the potential to transform the way we think about computation and artificial intelligence. It sounds like the future of computing is looking more and more like the brain itself.
Thank you, Bella. It's an exciting field, and I'm looking forward to seeing what the future holds.